Now we're going to take a look at the immune response to extracellular bacteria first and then viruses second. So here you have a very crowded slide that shows you multiple arrows and all sorts of things that are happening in response to bacteria coming in through broken skin. So here are the bacteria coming in. And I think it's probably better to just take a look at this in pieces. It's too crowded. So here we have skin that's broken and now bacteria coming in. And let's see what your body will do. So first response to this is that you have some inflammation going on. So pretty quickly after something like this happens, you will see that you're going to have some inflammatory swelling and probably some pain too. But you will activate complement proteins, and they will start making the membrane attack complex. That will start happening. They also activate mast cells, which then release histamine, which then causes the increased permeability. That would be the swelling part, and the increased blood flow, the heat of inflammation. They also act as chemotaxins, and they will then cause more white blood cells. So the chemotaxins, these are calling white blood cells to come over. So then these white blood cells here, macrophages, actually monocytes and mostly neutrophils, they will be stopping right here. There's increased permeability, so they can squeeze through here. That's called diapedesis, to go between these endothelial cells. They're sensing these chemotaxins, and they're coming over here, and they're starting to migrate into the area. Once that has happened, so now here our neutrophils are moving into the area, and these phagocytic cells, they will start to eat up bacteria. If you already have labeled bacteria, that makes it that much easier for your phagocytic cells to eat them up, but they will also find bacteria that just simply don't belong there, and your phagocytic cells will recognize that. Another thing that's going to happen is that plasma proteins will come in here. Some antibodies, perhaps, also acute phase proteins, and they will act as opsonins, labeling and coding these bacteria to help the phagocytic cells have an easier time with all of this. And so now here, back to our original slide, where we're putting it all together. So you have sort of defense from multiple sources. These bacteria coming in. The first thing, the immediate concern is that you want to localize this growth here of bacteria. You do not want these bacteria to go into the bloodstream, where they then would spread around the entire body and cause bigger problems. So you want to limit the inflammation, the infection here to this local area, and for that you have multiple pathways available. So we're starting complement, and then activate the mast cells with the histamine release, causing inflammation, the chemotaxins, calling other white blood cells, phagocytic cells, that then eating up the bacteria, also antibodies, acute phase proteins coming in, labeling the bacteria. So you're doing everything you can in order to limit this inflammation, infection to the local spot where the injury occurred. So now we're moving on to the immune response to viruses. And again, this slide is pretty crowded, summarizing all the different processes that happen. So we're better off taking a look at it step by step. So here we have the example of a virus invading the host. So the virus is coming. If you are lucky enough that you have pre-existing antibodies, it's great, because if they're there, then they will right away bind to the virus. And then what could happen, that several things. So here, if you have antibodies available, they will bind to the virus, and then the virus cannot infect another host cell. So here you have an uninfected host cell. Now here in this case, you didn't have the antibodies, and so now you have an infected host cell that starts to express these red triangles here, this viral antigen on its surface. Now, continue on with this here. So let's first move over in this direction. So here we have pre-existing antibodies, and now these pre-existing antibodies, they bound to the virus, and now the macrophage comes in and says, oh, okay, I'm going to eat all of this up here. Anything that's labeled with an antibody will be eaten by a macrophage. So the macrophage ingests the virus and says, oh, okay, the red triangle is pretty interesting. So I'm going to embed that into my MHC class 2 complex. And then here, the macrophage now becomes an antigen-presenting cell, starts secreting some cytokines that lead to inflammatory responses, also that antiviral responses via interferon alpha. Those antiviral responses are communicated via the interferon alpha to both uninfected host cells and the infected host cells, which is interesting. And so then here we're moving on now on this side over here. First, so this macrophage, this antigen presenting cell now will now form this bond here, or this has this helper T cell latch on to the MHC class 2 complex that has a red triangle embedded in it, and it will cause a helper T cell to go off and make a strategy, which typically involves that we're activating B lymphocytes, to become plasma cells and churn out antibodies. So we now are generating antibodies at a high rate once you have the correct antibody available, though. So this will take some time here. Typically, if it's something that your body hasn't seen before, then it will take the B lymphocytes up to about a week before it can make the correct plasma cells and churn out these antibodies. Meanwhile, these helper T cells, they will also activate cytotoxic T cells. Now, cytotoxic T cells, and they will then go after those virus-infected cells and kill them. So they will basically say, hey, you are beyond help, you are virus-infected, and we need to destroy you. So this infected cell will undergo apoptosis and will die here. So you can see here again this very central role of this interaction of an antigen-presenting cell with the helper T cell, because the helper T cell then activates the cytotoxic T cell, and it will also activate B lymphocytes to make the antibodies. So if you take out this central portion here out of your immune system, out of your immune response, because there are not enough helper T cells available, or they just died because of HIV infection, then basically none of this down here will happen, and your immune system, it's still there, but it's not doing anything because nobody's activating it. Let's talk a little bit about allergies. That is basically a overreaction of your immune system. So an allergy is an inflammatory immune response to a non-pathogenic antigen, an allergen. So basically your immune system is going after something that wasn't dangerous. It just mistaken it for a dangerous enemy, and it really wasn't dangerous at all. So a lot of times people also call this a sensitivity to something, or even hypersensitivity to something. There are different versions of allergic responses with different severity. Immediate hypersensitivity reactions, they are usually mediated by antibodies, and they occur within minutes, so they're very fast. Then we have delayed hypersensitivity reactions. They're mediated via helper T cells and macrophages, and they take much longer to develop. And then the most severe of all allergic reactions would be an anaphylactic reaction, where you have body-wide opening of blood vessels via histamine release body-wide, that then drops your blood pressure, and then you usually go into shock, so an anaphylactic shock. But let's take a look at what an allergic reaction could look like. So it takes 2 exposures for the full effect to take place. And in the first exposure, there is the allergen. It's nothing dangerous, but your immune system thinks it is dangerous. And so now your MHC class 2 antigen presenting cells go in activity. They're presenting the red triangle here that wasn't dangerous at this time to the helper T cell. The helper T cell activates B lymphocytes. They make antibodies eventually, and now you're going to well, let's see what happens at a second exposure. With the second exposure, right away you have activated T cells that churn out cytokines that lead to inflammation. Also, the antibodies are right away present, and they will bind. These antibodies will bind to that to the antigen, the allergen in this case, and that will activate complement proteins, leading to more inflammation. And then here you have these mast cells that start degranulation, releasing lots and lots of histamine out of these granules. And so these cytokines and histamine, they cause vasodilation, increased vascular permeability, so all the swelling, and guess what? More inflammation. So then you're dealing with the sneezing and the itching, and worst case scenario, you have anaphylaxis going on body-wide. That means your blood pressure will drop suddenly and you might go into shock, and it could be deadly. So here, allergic responses, sort of the summary slide. So again, the first exposure, nothing seems to happen, at least outwardly, but here the allergen is causing this phagocytic cell to become an antigen-presenting cell, and that sets in motion the T lymphocytes, and then eventually leads also to the formation of antibodies. At second exposure, these memory T cells, they get activated very quickly. They release cytokines. The antibodies will bind to the allergen and triggering more inflammation, and then on top of that you get mast cell degranulation, which releases tons of histamine, and so there you have a massive inflammatory response with all the symptoms that go along with it. Let's take a look at the types of antigens that we would find on our white blood cells and also on our red blood cells. For the white blood cells, the leukocytes, we have the MHC class 1 and class 2 complexes. So MHC proteins, we also call them human leukocyte antigens, HLAs. And again, we have the MHC class 1 and class 2 proteins. For red blood cells, we don't have any MHC proteins, but we're using the A, B, and, well, O is none of these antigens for the 4 blood types that we recognize. Type A blood, type B, AB, and O, which has neither A nor B. Then there's another antigen that's found on red blood cells. That's the Rh antigen, and we talked about this in the lab. In general, people express antibodies to the red blood cell antigens they do not possess. In other words, if I'm blood type A, then I typically have anti-B antibodies. So I would not be compatible with type B blood. But let's take a look at the what happens here. So in this chart, you can see the blood types here, O, A, B, and AB. And this is what the corresponding red blood cells would look like for that blood type. Blood type O has neither A nor B antigens. And the A antigens, they're the circles right here on this type A blood, and type B, we have triangles, blue triangles this time. And when you are blood type AB, then you have both the red circles and the blue triangles. You have the A and the B antigens. Consequently, the antibodies that will be found in the plasma. So if you are blood type O, then you're going to have anti-A and anti-B antibodies. If you are blood type A, then you typically have anti-B antibodies. If you're blood type B, then you have anti-A antibodies, so forth. And if you're AB, then you have neither A nor anti-B antibodies. Now let's take a look at this ABO blood group frequency table in the United States. The most common blood type is O, followed very closely by A. Then a lot fewer people have blood type B, and the most rare of blood types is typically AB, and you can take a look at the distribution by ethnicities, but we did this pretty much in the lab. So here is what happens when you have a mixture of type O with type A blood. And what you can see here is that the anti-A antibodies that were found in this plasma, so the plasma contained antibodies to group A or type A, they will now bind to the type A blood, and it will cause it to agglutinate, the clumping reaction that I mentioned in the lab to you. So the agglutination reaction is this clumping reaction where you have these multiple antibodies binding to multiple cells, and it causes this clumping reaction or agglutination. Now, we're coming here toward the end. Let's talk one more time about this all-important system of self-recognition. So the body must be able to distinguish self from foreign. And in general, the system works pretty well. But if the system fails, then there are some serious consequences to this. If the body, for some reason, thinks that a body-owned structure is something foreign that it should attack, then we call that autoimmune disease. And now you're aiming your own weapons. And these are powerful powerful weapons. You're aiming them against yourself, and that has serious consequences. And we'll pick it up from there in the next section.